Hello friends, welcome back to my YouTube channel. This is part number 13 of my discussion on adsorption. I will continue my discussion on stage-wise adsorption, and today I will be discussing a numerical that is based on single-stage adsorption. In my previous video, I had discussed all the theoretical aspects of single-stage adsorption. I had discussed how to get the equation for the operating line for a typical single stage adsorption operation, then how to plot the operating line on an equilibrium diagram. I'm giving link to the playlist of all my videos on adsorption in the description section. So let us begin the discussion. To begin with, we will look at the problem statement, the numerical example that we will be solving. The problem statement: 1 liter flask is containing air and acetone mixture at 1 atmosphere and 303 Kelvin. The relative humidity of acetone is 30%. 2.5 gram of fresh activated carbon is introduced into the flask and the flask is sealed. Compute the final vapor composition and the final pressure, neglecting the adsorption of air. The equilibrium data is given in the following table. So you have the equilibrium data with us. We have the equilibrium data. So it has different values for gram adsorbed per gram of carbon. All these are equilibrium values, and the corresponding equilibrium partial pressures of acetone, they are provided to us. So based on this, we are supposed to find out the final vapor composition and the final pressure, neglecting the adsorption of air. The vapor pressure of acetone at 303 Kelvin, it is given to us. It is 282 millimeter of Hg. So basically you have 1 liter flask that is containing air and acetone mixture. Total pressure is 1 atmosphere and temperature is 303 Kelvin. Initially, at the start, the relative humidity of acetone is 30%. And to this mixture, we are adding 2.5 gram of fresh activated carbon, which in this case is acting as the adsorbent, or is the adsorbent. 2.5 grams of fresh activated carbon is introduced into the flask, and then the flask is sealed. So after some time, we are supposed to find out the final vapor composition in the flask and final total pressure. And in doing so, we are going to neglect the adsorption of air. The equilibrium data is provided to us. And the vapor pressure of acetone at 303 Kelvin, it is also given to us. It is 282 millimeter of mercury. So first of all, we will list what is given to us, the given data. We have a mixture of two components. Which are these two components? Acetone, I am going to denote that by A, and air, I am going to denote that by B. So it is acetone air mixture. Acetone, it is to be adsorbed on activated carbon. So the adsorbent used in this case is activated carbon. There is adsorption of only A, that is acetone. Adsorption of air, that is B, we are neglecting it. The operation is to be carried out in 1 liter flask. So this is actually a single stage operation, because you are adding the adsorbent only once to the flask. So it is basically a single stage operation. The volume of the flask is given to us. It is 1 liter, and if I convert it to meter cube, it will be 10 to the power minus 3 meter cube. Pressure is given to us. It is atmospheric pressure. P is 1 atmosphere, that is 760 millimeter of mercury. Temperature is also given to us. Temperature is 303 Kelvin. Then initial relative humidity of acetone is given to us. I am denoting it as RHA, and it is 30%. So that means the relative humidity, what does it convey? It conveys initial concentration of acetone in the mixture. That means they have given initial concentration of mixture in the initial concentration of acetone in the mixture indirectly. They have given it in terms of relative humidity. We will have to deal with that. Then initial weight of the adsorbent is given to us. It is pure adsorbent. That's why it will be entirely the adsorbent solid, and we denote that by SS as per our notation. So SS in this case is 2.5 gram. Then vapor pressure of acetone is given to us at 303 Kelvin. I'm going to denote it as PA0, and it is 282 millimeter of mercury. The equilibrium data is given to us. So we have equilibrium values of gram acetone adsorbed per gram of carbon, and we also have the corresponding equilibrium partial pressures of acetone in the mixture. So equilibrium data is given in this form. We need to convert it to an appropriate form so that we can use it by solving the numerical. What are we supposed to find? We are supposed to find the final vapor composition, and we are also supposed to find the final total pressure in the flask. So based on all the given information, ultimately we are going to report these two values, the final vapor composition and the final total pressure. So let us move. Let us first look at what would be the approach for solving this numerical. So I'm calling it as the approach to solution. So first step would be we have to find LS and capital Y0. What is LS? LS in this case would be mass of air, mass of the unadsorbed substance, and in this case air is the unadsorbed substance. And what is Y0? Y0 is weight fraction of acetone in the mixture with air initially on a solitary basis, capital Y0. So first step would be we will be getting LS and Y0, LS and capital Y0. You please refer my previous video where I have discussed all the details of single stage adsorption. So first step would be we will be finding LS and Y0. LS in this case is gram of air in the acetone air mixture, and as I said, air is the unadsorbed component. Y0, what is Y0? It is gram of acetone per gram of air. That is weight fraction of acetone on acetone free basis initially. Y0 is gram of acetone per gram of air initially present. So we are supposed to get Y0. And how are you going to get Y0? Y0 we are going to get from percentage relative humidity, which is given to us. Then we need to convert the equilibrium data in an appropriate form. So what is given to us is gram of acetone adsorbed per gram of carbon. This is nothing but capital X. Weight fraction of acetone on acetone free basis on the surface of the adsorbent. So it is directly given to us. So there is nothing to do with this. You will use as it is. Then partial pressure of acetone is given to us. Partial pressure of acetone, I am going to denote it as PA, and we will have to convert it to gram acetone per gram of air. Gram acetone per gram of air is nothing but capital Y, which is weight fraction of acetone in its mixture with air on acetone free basis. So the only task is we will have to convert the partial pressures of acetone to capital Y. So we will do that. Then after we have the data in an appropriate form, that is we have X and Y values that are in equilibrium with each other, then you can go for plotting the equilibrium diagram, where we'll be plotting capital X on the X-axis and capital Y on the Y-axis. And after plotting the equilibrium curve, you will be plotting the operating line by knowing its slope. And finally, once you have plotted the operating line, you'll be finding capital X1 and capital Y1. So capital X1 and capital Y1, these values we are going to use to get the final total pressure in the flask and also the final composition, vapor composition in the flask. So I hope the steps that we are going to follow to solve this numerical, they are clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. Okay, now let us go for the solution. First step is we will be finding LS. Initial partial pressure. In order to get LS, first we will have to get few things. First is we will have to get initial partial pressure of A. I am denoting it as PAI. So for that we will be using the equation formula for percentage relative humidity. Percentage relative humidity is equal to PAI divided by PA0 into 100. Where PAI, as I said, it is initial partial pressure of acetone, which is given to, we will be finding that. PA0 is the vapor pressure which is given to us. Percentage relative humidity is given to us. Percentage relative humidity is 30. PA0 is 282 millimeter of mercury, the vapor pressure. So if I use these values, it will be 30 is equal to PAI upon 282 into 100. That is PAI is equal to 30 into 282 by 100, which gives me PAI as 84.6 millimeter of mercury. So in this way, we get PAI, which is the initial partial pressure of E. Now let us get initial partial pressure of B, that is PBI. So for that, I will use, we know the sum of partial pressures is equal to total pressure, the Dalton's law. So it will be total pressure is equal to PAI plus PBI, partial pressures of A and B, initial partial pressures of A and B. P is given to us, PAI, we calculated it, and we can easily get PBI. So it will, P is 760 mm of Hg, the total pressure. PAI is 84.6 mm of Hg, we just found out, and therefore it will be 760 is equal to 84.6 plus PBI. That is PBI is equal to 760 minus 84.6. That is PBI is equal to 675.4 mm of Hg. So in this way, we get initial partial pressures of the two components, PAI and PBI. Let us move ahead. Okay, so the next step is we will be finding initial moles of A and B. That is NAI and NBI, where NAI represents initial moles of A and NBI represents initial moles of B. So for that, I will be using ideal gas law. First, I will use it for the component A, that is acetone. So it will be PAI into V is equal to NAI into RT. PAI, we have found out earlier, it is 84.6 mm of Hg, but since the unit for pressure, it will decide the value of R. So if I have to use R as 8314, I will talk about it. Pressure has to be in Newton per meter square. So I have done the conversion. PAI is 84.6 mm of Hg. That is, if I divide it with 760, it will be converted to atmosphere. And if I multiply it with 1.103 into 10 to the power 5, it will be in Newton per meter square. And that is what I have done. So PAI is equal to 84.6 mm of Hg. That is equal to 84.6 divided by 760 into 1.103 into 10 to the power 5, which gives the value as 11276.3 Newton per meter square. Then volume is given to us, it is 10 to the power minus 3 meter cube. R, the value of R that I will be using in this case is 8314, and in that in the units with this values, the units with this value are meter cube, Pascal per kilomole per Kelvin. So volume, it is in meter cube, pressure it is in Pascal, that is Newton per meter square. So amount is in kilomole and temperature is in Kelvin. So after using this value, I will be getting NaI in kilomole. Temperature is given to us, it is 300 Kelvin. So if I put all the given values, it will be 11276.3 into 10 to the power minus 3. That is equal to NaI into 8314 into 303. That is 11276.3 into 10 to the power minus 3 divided by 8314 into 303. That is equal to NaI. That gives me NaI as 4.49 into 10 to the power minus 6 kilomole. And if I have to convert it to mole, I will have to multiply with 10 to the power 3. So that will give me NaI as 4.49 into 10 to the power minus 3 mole. 10 to the power minus 6 into 10 to the power plus 3. It gives 10 to the power minus 3. So NaI, initial moles of A in the flask, they are 4.49 into 10 to the power minus 3 mole. Now let us get initial moles for B, that is NBI. So for that we will be using ideal gas law for B, which is PBI into V is equal to NBI into R into T. PBI we found out earlier, it is 675.4 millimeter mercury, and I will be converting it to Newton per meter square. So it will be 675.4 divided by 760 into 1.103 into 10 to the power 5, which is 90023.7 Newton per meter square. Volume is 10 to the power minus 3 meter cube. It is given to us. R is 8314 meter cube Pascal per kilomole per Kelvin. Temperature is again 300 Kelvin, 303 Kelvin. So it will be 90023.7 into 10 to the power minus 3. That is equal to NBI into 8314 into 303. That is 90023.7 into 10 to the power minus 3 divided by 8314 into 303. That is equal to NBI. That gives NBI as 3.57 into 10 to the power minus 5 kilomole. That is NBI will be 3.57 into 10 to the power minus 2 mole. If I multiply with 10 to the power 3, it will be 3.57 into 10 to the power minus 2 mole. So in this way, now we have got initial moles of A and initial moles of B. So let us move it. Now we will find initial masses of A and B. So MAI, the initial mass of A, and MBI, the initial mass of B. So for that, I will use the defining equations for number of mole. Defining equation for number of mole. What is that equation? NaI is equal to MAI divided by capital Ma, where capital Ma is the molecular weight. So that means MNI is equal to NaI into Ma. So NaI we have found out earlier, it is 4.49 into 10 to the power minus 3 mole. Ma, capital Ma, that is molecular weight of acetone is 58. So that gives me MAI as 4.49 into 10 to the power minus 3 into 58, which gives me MAI as 0.26 gram. Now let us get initial mass of B. So for that, number of moles of B, that is NBI, is equal to MBI divided by capital MB. That is MBI is equal to NBI into MB, capital MB. NBI we have got just now, it is 3.57 into 10 to the power minus 2 mole. Then the molecular weight of air, we are taking it as 29. So capital MB is 29. So therefore MBI will be equal to 3.57 into 10 to the power minus 2 into 29. That gives me MBI as 1.04 gram. So in this way, now we have got masses of A and B, initial masses of A and B. Now, how to get TLS? Finally, you can get TLS. As I said, TLS is mass or mass flow rate of the unadsorbed component. And in this case, the unadsorbed component is air. So LS is nothing but initial mass of air that is present in the mixture. That is LS is equal to MBI, which is nothing but 1.04 gram. So in this way, we complete our calculations for step number 1. Finally, we have got the value for ELS. Let us continue. Okay, so next is we will be finding X0 and Y0. Since we are using pure adsorbent, it will not be containing any acetone on its surface initially. That means weight fraction of acetone on the surface of the adsorbent is 0, or weight fraction of acetone in the adsorbent phase, initial adsorbent phase, it is 0. That is, small x0 is 0, which means capital X0 is also equal to 0. What is capital X0? I have discussed it in my previous video. I have given link to the playlist which has all my videos on adsorption in the description section. If you have not yet seen those videos, you please watch those videos. Y0, it is calculated in this way. So this is simply mass of A initially, that is initial mass of A divided by initial mass of B. This is weight fraction of A on A free basis initially. So again, I have discussed this in my previous video. You please watch it. So Y0, capital Y0, we are going to calculate it by this simple formula, MAI divided by MBI. MAI we had calculated earlier, it is 0.26. MBI we calculated it, it is 1.04 gram. MAI is 0.26 gram and MBI is 1.04 gram. So if you use those values, capital Y0 will be 0.26 divided by 1.04. That is, capital Y0 comes out to be 0.25. Now, let us modify the equilibrium data. As per our requirement, we will be modifying the equilibrium data. The equilibrium data, in that data, equilibrium X values, they are directly given to us, because gram acetone adsorbed per gram of carbon is nothing but X, and values of this quantity, equilibrium values of this quantity, they are given to us. So there is no need of doing anything with these values. What we have to change is the other value, partial pressures. We will have to convert partial pressures to capital Y. So capital Y, it is defined as gram of acetone per gram of air, and this is nothing but mass absolute humidity, mass of acetone divided by mass of air. It is mass absolute humidity. I am going to denote it as HA. So in this case, Y, which is defined as gram of acetone per gram of air, it is nothing but humidity, mass absolute humidity of acetone. So this is HA. Now HA is the mass absolute humidity, as I told you, mass absolute humidity of acetone. So let us continue with. Okay, so we are modifying the equilibrium data. Equilibrium X values, they are directly given to us. That is gram acetone adsorbed per gram of carbon. This is X. So there is nothing to do with this. Now what we have to do is we have to get Y. What is given to us is partial pressure. So we are going to get Y from partial pressure. Y, it is defined as gram of acetone per gram of air, and this is nothing but mass absolute humidity of acetone. HA, this is mass absolute humidity of acetone. Now HA, it is given by this formula. HA is equal to partial pressure of A, that is PA, upon partial pressure of B, that is PB. Partial pressure of acetone divided by partial pressure of air into molecular weight of acetone divided by molecular weight of B. So this is mass absolute humidity of acetone, which is nothing but capital Y. So that means from the partial pressures, we can get Y values. So let us do that. Now capital Y is equal to the mass absolute humidity, and this is equal to PA upon P minus PA, because there are two components, and PA plus PB, we know this. Now according to the Dalton's law, partial pressure of A partial pressure of A plus partial pressure of B is equal to total pressure. That is, partial pressure of B is equal to total pressure minus partial pressure of E. So I have used this relation over here and I'm getting this equation. So capital Y, which is mass absolute humidity of acetone, is equal to partial pressure of A divided by total pressure minus partial pressure of A into molecular weight of A divided by molecular weight of B. So now equilibrium values of PA, equilibrium partial pressures are given to us, and that by using this equation you can convert equilibrium partial pressures to equilibrium Y values. So these are converted to equilibrium Y values by using this equation, and we are going to do that next. So as I said, we will be converting the partial pressure data to absolute humidity data. So we have different values for gram acetone adsorbed per gram of carbon, which is nothing but capital X. Then you have different values of partial pressures of acetone, that is PA, which is given in mm of Hg. And then we are going to calculate corresponding Y values using the value of PA by using this equation. Y is equal to PA upon P minus PA into MA upon MB. So different values for capital X are 0, 0.1, 0.2, 0.3, 0.35. Corresponding partial pressure values are 0, 2, 12, 42 and 92. And when I use this formula for each of the value of partial pressures, I will be getting corresponding values for Y. So in that equation, Ma, which is molecular weight of acetone, it is 58. Then Mb, which is molecular weight of air, it is 29. So if I use this formula, I will be getting capital Y values: 0.0053, 0.0321, 0.1170, 0.2754. So in this way, I now have X values and Y values that are in equilibrium with each other. So next, I can use these values to plot the graph and then plot the operating line. Let us move ahead. Okay, so now we will be plotting the graph. So I have chosen a scale, the same scale on both the axes. And on x-axis, I will be plotting capital X. On the y-axis, I will be plotting capital Y. And if we plot equilibrium XY values, we will be getting a curve like this. This curve is nothing but the equilibrium curve. After plotting the equilibrium curve, the next task is we will be locating point x0, y0. So x0 is 0 since we are using pure adsorbent. Capital Y0 we have calculated it earlier. It is 0.25. So the point will be located on the y-axis where y is 0.25 over here. It is y0. The operating line will be starting at this point. Now let us plot the operating line. For plotting the operating line, we will be using its slope, which is given as minus SS upon LS. SS is given to us, it is 2.5 gram. We had calculated LS earlier, it is 1.04 gram. So if you use these values, we will be getting slope as minus 2.5 divided by 1.04, which gives us the slope as minus 2.4. So we know that the line will be having a negative slope. So for plotting the line, since I am using the same scale on both the axes, I can use the definition of tan theta. So you know, slope of a line is tan of the angle it makes with the horizontal. So if this line is making an angle of theta with the horizontal, then its slope is equal to tan theta. Now if I complete the triangle, which is the right angle triangle, and if this side measures m and this side measures n, then the definition of tan theta in this triangle is m upon n. And if I make n to be 1, then in that case tan theta will be equal to m. So the same thing I will be using this definition I will use for plotting the operating line. So since I have to plot a line of negative slope, I will be traveling 1 unit distance. I will be traveling in a downward direction. So the operating line should start. It is starting at this point. So if the denominator is to be 1, that means this distance will be equal to y. So I will travel a distance of 1 unit towards the right of this point. And since I want to plot a line of negative slope, instead of traveling in upward direction, I will be traveling in a downward direction. But what is the distance through which I will be traveling? The distance is equal to slope, because here we have made the denominator 1. So this is 1 unit, and now I will travel the units that are equal to the slope in vertically downward direction. So since slope is 2.4, so I will be traveling a distance of 1, 2 and 0.4. So this will give me a line of negative slope. Since I have to plot a line of negative slope, I am traveling in a downward direction. You can of course use protractor to plot the line, but if you are using a graph where the scale on both the axes are same, then you can use the definition of tan theta. So I get this point. Now the next task is I will be plotting a line from this point, allow it to pass through this point, and then it will intersect the equilibrium curve. So the point of intersection is nothing but x1 and y1. So y coordinate of this point gives me y1 and x coordinate of this point gives me x1. Now I can easily read the values of x1 and y1, and after reading those values, I will be using those values for my further calculations. So let us move ahead. Now from the graph, if you check, x1 is 0.1 and y1 is 0.053. Luckily, the line intersects the equilibrium curve at a point which is given to us. So for that point, x1 is 0.1 and capital Y1 is 0.0053. Okay, so after getting the values of x1 and y1, we will first find out the final vapor composition. So from the graph, we have got capital X1 to be 0.1 and capital Y1 as 0.0053. Now, the final vapor composition, we are going to get it by using the values of the value of capital Y1. Capital Y1, it is gram of acetone per gram of air. Capital Y1 is nothing but gram of acetone per gram of air. Finally, we know that value, it is 0.0053. In this case, gram of air, it remains unchanged. So, gram of air, initially, it remains unchanged during the operation. Therefore, gram of air is equal to LS, which is 1.04. We had calculated it earlier. It is not going to change. It will remain as it is. So, gram of air is 1.04 gram. Now, gram of acetone divided by gram of air, which is 1.04. That will be capital Y1. That is capital Y1, which we know it is 0.0053. So this is nothing but, just a minute. This is nothing but capital Y1. So how it is defined? How is capital Y1 defined? Gram of acetone per gram of air in the final mixture. So in that we know gram of air because it remains unchanged. So therefore it is gram of acetone divided by 1.04, that is equal to 0.0053. that is gram of acetone, will be equal to 0.0053 into 1.04. That is gram of acetone will be 0.00512. So finally, the final vapor will contain 1.04 gram of air, which has remained unchanged, plus it will contain 0.00512 gram of acetone in it. So that is answer to the first question. Now let us get answer to the second question, which is the final total pressure. So for that, we again will use the value of Y1. Y1 in terms of partial pressure, it will be defined as capital Y1 is equal to PA1 divided by P minus PA1 into MA upon MB. Y1 we have calculated it. We have got it from the graph. It is 0.0053. MA, molecular weight of acetone, is known. MB, molecular weight of air, it is known. So total pressure is known to us. It is 760 mm of Hg, that is 1 atmosphere. Molecular weight of acetone is 58. Molecular weight of air is 29. Now you simply have to use all these values in this equation and get the value of PA1. Okay. So we have this equation for Y1. Y1 is equal to PA1 upon P minus PA1 into MA upon MB. Now our task is to get PA1. Y1 is known to us. It is 0.0053. We have got it from the graph. Then P is known to us. It is 760 mm of Hg. Molecular weight of acetone, that is MA, is known to us. It is 58. Molecular weight of B, that is air, it is known to us. It is 29. So therefore, if we use these values in this equation, it will be 0.0053. That is equal to PA1 upon 760 minus PA1 into 58 by 29. So that is 0.0053 divided by 58 into 29. That is equal to PA1 upon 760 minus PA1. I have rearranged the equation. So that is 0.00265. So this is 0.00265. That is equal to PA1 upon 760 minus PA1. In the next step, I'll bring this bracket to this side. So it will be 0.00265 into 760 minus PA1. That is equal to PA1. Let us solve this bracket. So it will be 2.014. 0.00265 into 760 is 2.014 minus 0.00265 into PA1. That is equal to PA1. So in the next step, I'll bring this term to this side. So it will be 2.014. That is equal to PA1 plus 0.00265 PA1. That is 2.014 is equal to 1.00265 PA1. That is PA1 will be equal to 2.014 divided by 1.00265, which gives me PA1 as 2.009 millimeter of Hg. Therefore, the partial pressure of air, we know that partial pressure of air, it remains unchanged because it is not going to get adsorbed. So therefore, PB1 will be equal to PBI, which is 675.4 millimeter of Hg. And now we can get the final total pressure, which is P is equal to PA1 plus PB1. PA1 is 2.009, PB1 is 675.4. That gives us P as 677.41 millimeter of mercury. So that is the answer to the second part. So they had asked us to find the final vapor composition. We have found the final vapor composition, and they had also asked us to find the final total pressure, and we have got the final total pressure. It is 677.41 into Hg. Now you can easily understand that the total pressure has reduced from 760 to 677.41. What is the reason for that? The reason is some of the acetone, it has adsorbed on the surface of carbon, that is adsorbed. So with this, I end my discussion. We have got answers to all the questions, and with this I will end my discussion for this numerical. I hope you have understood the steps that I have used for solving this numerical. If you have any doubt, you please mention them in the comment section. Thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to it. hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Thanks for watching. Have a nice day. Hope to see you soon in my next video. In my next video, I will be discussing multi-stage cross-current adsorption operation. So be with me in my next video. For now, have a nice day. Thank you. Bye-bye.